Well, good morning, everybody. We're back. I hope you had a wonderful but safe holiday season. My name is André Tétreault, and I'm director of the Tests and Diagnostics department here at Vibrosystem. I am also very happy to see that my colleague Paul Amelinckx is also back. Paul, as you know, is one of our analysts here at the Tests and Diagnostics department. And as usual, he'll be handling all the logistics, and also will be handling any and all questions in Spanish and or Portuguese. So good morning, Paul.
Good morning, buen día. Thank you, André. Hello, everyone. Buen día a todos. It's good to be back after a while. For our friends in Latin America, Brazil, Spain, and Portugal, please feel free to submit your questions in Spanish or Portuguese. We will be glad to answer them as well. Para nuestros amigos en América Latina, Brasil, España y Portugal, ustedes bien pueden formular sus preguntas en español o en portugués, las que responderemos con mucho gusto.
So, good morning, everybody, and welcome to our 9th Q&A session live on YouTube, directly from our head offices here in beautiful Montreal, Quebec, Canada. I'm very happy to be here with you this morning to discuss, among other things, hydro generators, but especially today, we're going to discuss web-based monitoring centers. So we've basically kept the same format today as we used in the last Q&A session, which basically is to have a presentation which will last maybe 20 or 30 minutes. During that presentation, feel free to ask any questions. Paul will log them and we'll take a look at them after the presentation is over. So this week's presentation is about web-based monitoring centers.
Remember that to be able to submit your questions during the Q&A session, you need to log on to your YouTube account. As mentioned in previous sessions, we make sure that all questions asked previously are answered today. We will answer the remaining questions at the end of the session if we have time. Recuerde que para poder enviar sus preguntas durante esta sesión, usted necesita ingresar con su cuenta YouTube. Tal como hemos mencionado en anteriores sesiones, es nuestro objetivo que todas sus preguntas anteriores sean respondidas el día de hoy. Sin embargo, si tenemos tiempo para responder todas las preguntas del día de hoy, lo haremos durante esta sesión.
So without further ado, let's start with our presentation. The presentation in reality shows the evolution of monitoring solutions for generators over time. So let's take a look.
Okay. Just a sec. There you go.
All right, so generator diagnostics as an asset management tool. Generator condition monitoring systems are widely used today, but unfortunately, maybe understandably, this has not always been the case. Over time, solutions have evolved significantly from basic just measuring chains used during commissioning to having these measuring chains connected to PLCs for trending and protection, and all the way to sophisticated diagnostic systems which are common today. Before actual, what we call monitoring, and we'll see there's a difference in our terminology, before the actual monitoring was used, measured parameters were limited to basic operational data, such as stator temperature, bearing temperature, speed, rotor, stator voltage and current, active power, reactive power, humidity, all kinds of different parameters. But this approach was exclusively for operational use. It wasn't really for condition-based monitoring as we know it today. Health assessment or condition-based operation was not common because, quite simply, the tools and in some cases the expertise was just not available. Offline tests were used. Offline tests and measurements were performed usually during the assembly prior to the commissioning of the unit. So as the unit was being assembled, they would test various components statically just to see if they met structural constraints, insulation constraints, and so forth. Some of these tests were performed prior to the return to service stages after major outages or after minor or sometimes major repairs. These were mostly performed by OEMs or highly specialized consultants and engineering firms. So we have a picture here of a portable system. We have on the left a few vibration probes, X and Y. And on the right, we can see a portable system hooked to these sensors to take some readings. So the portable systems consisted of simple basic measuring chains installed and used for commissioning purposes only. These included shaft vibration probes, guide bearing absolution vibration probes, accelerometers or velocimeters, PD acquisition devices. Usually the couplers were installed permanently, but companies would come in and take PD readings at specific times. And of course the portable recording devices, which basically were oscilloscopes or their ancestors. I think Paul has memories of that as well, using oscillographs, where you would see a whole length of paper being produced with corresponding measurements. Usually were used for vibration. Now, in most cases, these systems were quickly removed after commissioning, making this solution unreliable because decisions were made based on limited data and specific time frames, sometimes different months, different seasons, or even years. And the data was potentially retrieved while the unit was in different operating conditions. No data was recorded between these testing periods. Therefore, the results could be incompatible or insufficient. In reality, you might miss something while you're not taking readings. Surprisingly, or in my opinion, shockingly, some owners still use this portable system approach for many parameters to this day. So then, from portable systems, the introduction of permanent systems happened. The evolution of monitoring systems was not only spurred on by a need to better protect the assets. As I mentioned before, most of these equipment were set up to be protection equipment. There was a protection scheme, alarms would be tripped and people would get involved. It's not only the need to better protect the asset by adding more reliable and efficient measuring chains along with more advanced acquisition devices and then on to the existing PLC systems, but it was also spurred on by a need to better understand what the monitoring systems were providing as data. So now we get into a monitoring or a diagnostic scheme. So this information could be used for operation and maintenance needs. Now, even if a permanent system is installed, it's not enough just to get signals from, on the left, we have some existing technologies, and this was before your time, Paul. I can see the older, or what people politely call vintage equipment. The systems that I installed when I began here at Vibrosystem 25 years ago. So we had existing technologies, let's say technologies that were invented from the 50s to the 80s. We're talking about temperature probes, relative vibration probes, absolute vibration probes, and then on to more recent technologies like equipment that was designed in the 80s and 90s. We're talking about air gap sensors, fiber optic accelerometers, or fiber optic temperature probes, shaft voltage monitoring equipment, partial discharge monitoring equipment, stray flux, and so on and so on. So all these signals were permanently connected to PLCs and later on to SCADA systems for trending and archiving through historians. But this only warns the operators if the variations, whether they're increases or decreases, are present, and establishes limits of operation. It doesn't allow for a comprehensive in-depth analysis. If thresholds are breached, experts still need to be called in to investigate. So this approach is considered by many as monitoring, but for us, we call that trending. So, introducing the diagnostics part of the equation, permanent systems allowed, because of the introduction of increased computing power and improved communication technologies, this allowed for more advanced diagnostic tools. The hardware and software tools were introduced, starting with the old DOS-based systems, which I used when I began here again, up to the present Windows-based systems, and in some cases other OS, other operating systems, of course. Now, despite these advanced technologies, expertise was still necessary to properly analyze the data. As time went on, data interpretation services evolved. These services were mostly offered by monitoring system providers. We began giving data interpretation services a long time ago. OEMs will do so, engineering firms, consultants. And although system interaction training courses were always offered, we always had people on site during the commissioning that would give training courses to the personnel on site as to how to use our Zoom system. And I assume other OEMs do the same. These usually fell short because manipulating the systems and obtaining data was insufficient if the users did not understand the data. So people would take readings and they would see sine waves, they would see results on the screen, but they had no idea what it meant. So it became necessary for system providers such as Vibrosystem to offer data interpretation training courses as opposed to simply monitoring system operation courses. And I've done that for many, many, many years, and although it's helpful, unfortunately, as is the case for many utilities, personnel move on. They move on to other departments, other plants, other companies. So the training efforts in many cases were not as effective as hoped. There was a tremendous amount of people, very highly trained people that were doing other jobs. So the next interesting step for generator diagnostics was the emergence of remote or fleet-wide monitoring centers. This approach allowed for the installation of monitoring systems at site with minimal training to plant personnel. The plant personnel were not asked to actually look at the results. All they performed was maintenance. So maintenance training was offered to make sure that they knew how to make sure the system was working properly. This approach also allowed the asset owners to concentrate all their expert personnel in one remote monitoring center, usually structured with 3 levels of intervention. And we've helped a few very large utilities to set up these types of monitoring centers. The 3 levels are, first and foremost, if there's data coming in, is the data valid? Second, if the data is determined to be valid, what is the data saying? What exactly are we looking at? And if the issue is significant, then the 3rd level of experts would come in, the intervention level, where they would decide what's required for each particular case. Do we need to shut down the unit? Do we need to lower the power? What do we need to do? This is quite common. And finally, the new approach is web-based monitoring and diagnostic platforms. We introduced a platform a few years ago, which turns out to be very, very popular. It's called a ZOOMWatch platform, where we offer diagnostics services through the web. And if I can just take a few seconds here, I'll just go to the website. I encourage everybody to log on to that website. It's called ZOOMWatch.com. And basically, it's a demo. It's not an app. You can go with your phone. It's just a platform. It's not an app. It's not going to install anything on your computer. And you can get a feel for what the platform looks like. If I select hydroelectric, you can see any utility can have their whole fleet of units here, and each unit is assessed periodically with newly retrieved data, and we assess the operability of the rotor, of the stator, and shaft and bearings when we're looking at hydro generators. So each operability level can be trended. You can see this is real data, by the way. You can see that the operability was going down, which means that the unit was performing less and less efficiently. And you can see there's a break pattern here where the user actually stopped the unit to make some corrections, and when they started the unit back up again, the results improved. And for each section, you have access to all the different parameters, different phenomena, that we will monitor on a hydro generator. For example, rim expansion, circularity, pole radial position, concentricity, pole overheating, stiffness issues, and shorted turns. And each of these is also trended so that you can see the evolution of the phenomena. And if you click at any point here, you have access to the actual report. Okay, so if any of you is interested in taking a look at this platform, it's a demo. Again, you can look at the turboelectric, and you can also look at the mining section. And all of these are available at ZOOMWatch.com. So, if we go back to the presentation, So web-based centralized monitoring systems allow for the concentration of information in one location. And also the platform allows for the display of simplified results. I mean, you can look at how the vibration is evolving on any particular unit without having to understand FFTs, spectral analysis, without having to understand orbits, phase, or anyone can look at the severity level of a parameter and see if it's going up, we have an issue, and then you can either ask us to explain the reasons why the severity is going up, and then you can ask your own experts, or you can ask the OEM or consultants or engineering firms to come in and try to resolve the issue. Okay, so we have a slide here showing a turbo unit, and also the system comes with an alarm service. So if alarms occur on site, our team here is notified immediately, and we have a chance to take a look to see if it's a severe alarm that needs immediate intervention, or if it's a spurious spike, which is not a real alarm, or we'll give you information on that alarm within an hour if it's a danger alarm, within 2 hours if it's a alert alarm. Okay, so web-based centralized monitoring systems allow users to view results, as I mentioned before, operability levels. These are assessments of various sections of the unit, accompanied by intervention recommendations, if any. So as I mentioned before, you could see on the hydro generators, there's 3 main sections. There's the rotor, the stator, and the shaft. The values represent the overall operability of any given section of the unit based on the severity levels, which I'll get into, for each phenomenon monitored associated to that section of the unit. Okay, so if you go on this slide, you can see that the rotor has an operability level of 92%. The stator has a level of 64%, and the shaft and bearings have a severity level of 84%. Okay, so this is based on data that's retrieved. In some cases, customers want new reports every month. Some of them are asking us reports every week. Most common is reports every 3 months, and they can go into the site and see how their units are evolving. Okay, so you can see here the operability level, as I mentioned before. You can see that don't need to be an expert to see that the results are going down. So you might want to put some effort into finding out what's going on and what to do about it. And severity levels are actual severity for each particular phenomenon on the asset. Okay, we have an example here for a turbo unit. This unit, we're monitoring the stator core and frame attachment system, the stator bar wedging system, the end windings and support system. The stator core deterioration on this unit was not monitored, and the stator bar deterioration. So each of these gets a grade based on the most available data, in addition to past data. So we're not only looking at snapshots, but we're looking at the evolution of the behavior. And when you do have an issue, there's an expert comment that will tell you why the value is what it is. So we can see here end winding vibration levels have deteriorated after 3 months of operation following corrective actions which were undertaken. So based on the available information, we estimate critical levels will be reached in approximately 8 months. So we recommend continued close monitoring so as to detect any sudden or slow evolving increases, and we recommend a visual inspection, especially in the area where the corrective actions were undertaken. So there's some information there that will help you take corrective action, or best case scenario is when you do have an outage coming up, you can use this information to better plan your outage. Okay, so we can see in this case the severity is going up, which is bad. When you see the operability going down, that's bad. If you see the severity going up, that's also bad. Okay, again, comments, recommendations for each result. And again, if you click on any of those dots, because each of those dots is based on data that was retrieved and analysis that was performed and reports were produced. So at any given point, you can click on any of these results and get access to a complete report which will explain what the results were, why the values are such and such, so it gives you a better perspective on the overall situation of the unit, or as we see in many contracts now, we have power stations that are giving us contract for multiple units so that we can help them better manage their assets. And that's it for the presentation.
Thank
Do
you,
we
André.
have any
that
questions?
Was quite interesting.
Thank you.
Now let's see what questions we have. Yeah, we have here. Okay, do you have any examples of return on investment ROI cases?
Oh, well, yeah, we have quite a few. In fact, I've written, I think, about 25 papers so far. Most of them are hydro and turbo generators, and we have quite a few cases where the return on investment was huge. One case that comes to mind was in the northwestern United States, where the utility suspected they had some serious rotor rim issues with their vertical hydro generator. And they had planned, I think it was 9 months down the road, they had planned a major refurbishment work. In fact, they were replacing the stator. Stator was quite old, and they felt it needed to be replaced with a new one. So the engineer on site said, well, we suspect we have rotor rim issues. We have reasons to believe so. They had mechanical telltale devices, and they were showing some movement. So they felt that they were suffering from a rotor rim looseness issue. And this engineer decided, well, we have time. Why don't we put some sensors in there, air gap sensors, and do some tests and ask Vibrosystem if they can tell us if the suspected rotor rim looseness issue was correct. So the sensors were purchased and installed, and we did a whole series of tests, what we call the RIS test, which is the Result Interpretation Service test. So we put the unit through all the different operating conditions. And after looking at the results, we found that the rotor was fine. There was no looseness, there was no shape variations, there was absolutely no source of concern or any result leading us to believe that there's a rotor rim looseness issue present. However, we did tell them that the rotor was not centered in reference to the stator, and that, as I covered in my training courses, and I think I've covered in past Q&A sessions, causes all kinds of issues, short-term, mid-term, long-term problems with the unit. So we told them that it strongly recommended that they correct the rotor offset problem. And we said, well, since you plan on replacing the stator, if possible, you might want to put the new stator offset somewhat, and it was in 90-degree direction, to compensate for this problem. And we also told them that the combined guide bearing was in very bad shape. We observed high peak values. We spotted multiple cases where we had what we call skating, which is a low frequency displacement. It's a displacement that's actually at a slower speed than the rotation of the unit. And which is quite uncommon. We also noticed that in most operating conditions, the unit suffered from negative orbits, which is, to put it simply, the shaft, the center of the shaft, moves in a direction that is opposite to the actual rotation direction of the unit. And in fact,
it's like skating backwards.
Yeah. And we discussed last week where when you do have that case, for us, when we look at data and we see negative orbits, our first reaction is the sensors are cross-wired. Because if you take a 90-degree and a 0-degree sensor and you either configure them opposite or you cross-wire them, that's exactly what you get. But we quickly noticed that this negative orbit issue was not always present. Sometimes it was in the correct direction, sometimes it wasn't. So we knew it wasn't a cabling issue or a configuring issue. So we told them we gave them all this information, and we said, well, you might want to think about moving the stator somewhat to resolve the issue of the center, mechanical center and magnetic center being different. And you might want to invest money in your combined guide bearing because we feel it's about to fail. So that's what they did. They replaced the stator, slightly offset. They performed some work on the rotor, was basically just removing the poles and cleaning, but they didn't reshrink, they didn't do any major works to the rotor because they were not required. And they took that money and spent it on, I forget if they replaced or they repaired the combined guide bearing. So when the unit was put back online, we did all the same testing again, and the rotor was fine. It was no longer offset. The vibration went down. No negative orbits anymore. No skating. Everything was back to the way it was. So this customer saved a lot of money by fixing things that were actually broken or going to break, and did not spend money fixing things that were not broken. So I think that's a perfect example of using information to better manage your asset, better plan your outage, make sure you have the parts you need, make sure you have the resources you need to go in there and fix actual problems that are there instead of fixing things that are not broken.
And we have another question here. Why decide to use capacitive displacement probes as opposed to inductive probes?
That's a common question. I think the other than the fact that my perspective is that the capacitive probe is more precise, the real reason why it's a better option, with the exception of a few constraints, is that the capacitive probe does not require calibration or tuning. The capacitive probe creates an electric field. So it doesn't really matter what type of metal is in front of it. It can be any type of metal. The reaction, the performance will be exactly the same. So you don't need to see, well, how is my sensor going to measure if it's facing brass or steel or different types of steel, iron, manganese, zinc, whatever material your shaft is made of. You'll have the exact same performance. Whereas inductive probes, depending on the type of material, you'll have a very different response from your sensor. So each individual sensor has to be calibrated for its location. So if you have 8 sensors, you have to calibrate all 8 of them, and you have to calibrate for their location and the material that will be facing the sensor. That has to be done. Now, once that's done, and our technicians know how to do that, it's fine. It works fine. But if you're using a capacitive probe, you don't need to worry about that. It doesn't matter. Now, there are some constraints, of course, if the area where the sensors are going to be installed is suffering from oil splashes all over the place, or carbon accumulation, or dust, or that will affect the capacitive probe. But that's rare. Usually, capacitive probes are always a good solution, but in some cases, they're not. So, to answer the question, capacitive probes, in my view, are more precise, and you don't need to worry about tuning or calibrating. You just gap the sensor at 1.3 millimeters, and there's no conditioner. The cable can run all the way to your acquisition unit, and you're ready to go.
Now we have another question from Mark Bissonnette. Have you seen cases where a forced outage or problem that affected the machine's condition would have been observed with the monitoring data well in advance, but was not being looked at by the owner?
Yes, we, of course, again, information is power. There are many cases where people focus on different things. For example, the case I mentioned before, magnetic center, mechanical center, that causes all kinds of issues. Issues like overheating poles, dovetails that will crack, rims that will crack, stator bar vibration. I mean, an offset rotor causes an uneven magnetic field, and that causes all kinds of problems. And in most cases, those issues are not only left unchecked, but I mean, nobody's even aware that the problem exists, because most people look at the vibration results that go into their SCADA system or go into their PLCs and look at it from the perspective of peak displacement, which is important, of course, because it's how severe the shaft is moving, and there are tolerances for that. But if you have a rotor that's not centered, when you apply the field, that rotor will shift to where the magnetic field is strongest, and that's where the air gap is smallest, and it will stay there. So it's magnetically coupled. The unit is almost unable to move. And that will create much lower vibration readings because it's actually stuck on one side. It can't move. So if you look at the vibration rack and you see the vibration very, very, very low, everybody goes, that's fantastic. We have a very good unit. But in reality, you don't. You have a unit that's not vibrating, but is vibrating because there's a serious problem. And that, again, that phenomena will cause all kinds of issues. I remember a case in the States, again, where a pump storage power plant had air gap sensors. And we did some testing, and I told them that one of the units had a serious magnetic offset issue. I was surprised that the bearing did not heat up, and because the shaft is up against the bearing in that location as well. And I told them that they should do a visual inspection of the rotor rim, the pole dovetails, to make sure there's no structural issues. And a few weeks after the report was published, they called us and asked us, why did you say that? And I said, well, we can see that the unit is offset and it's causing varying magnetic as the poles rotate, they're exposed to a very high magnetic field and then to a low magnetic field and then back to a high magnetic field. And introducing that variation in magnetic pole produces a tremendous amount of stress on all the mechanical components.
And fatigue.
Sorry?
And fatigue.
Yeah, metal fatigue. So I said, because of that, you should pay close attention to your visual inspections and say, what do you ask? I said, well, we did an inspection of that unit, and most of the dovetails were cracked. And they inspected the other units, they had 4, and the other ones did not have that issue. Well, the other ones were centered. Only this one was off-centered. So I said, hadn't you noticed this before? He says, well, when we do visual inspections, there's visual inspections and there's visual inspections. There's inspections that last a few minutes and there's inspections that last quite a few hours. So that's another tip. If you do visual inspections, do them correctly. Don't rush through them, assuming that everything is fine. You might be surprised if you look at the fine details what you will find. So yeah, there's quite a few cases where issues were raised, observed, analyzed using data that the customer was completely unaware of and totally surprised. And we've helped quite a few utilities either enforce warranty issues or be able to stop a unit and prevent failure. We had a case a few weeks ago in Latin America where the customer used the data from our report to stop a unit because they were very close to having a rotor stator rub. And they're using the information from our reports and from our Tests and Diagnostics department to help them try to fix the issue. So yeah, we do have quite a few cases like that.
Thank you, André. We have another question here. Why would pole faces heat up because of uprating the unit?
That's a good question. We actually have a product for that, which we call a ZOOMWatch rotor, where you can put an infrared probe. We suggest at 3 different levels through the ventilation holes of the stator to actually look at the pole face temperature, or in some cases look at the pole interconnection temperature, and see how the pole heat, I guess, results are. The reason for that is because in many cases, and I think a lot of cases where we've sold this technology was after a uprating of the unit. They usually will change the turbine to get a little more power out of the water flow. They'll get 3, 4, 5%, which seems like little, but if you put that in megawatts over a year, that's a lot of money. And by doing that, however, you are increasing the electromagnetic stress in the air gap. Okay, in fact, it's like the electromagnetic war between the rotor and the stator. You're introducing higher levels of electromagnetic stresses, and that can heat the pole face to some extent, especially if you have a stator that is not round. Okay, now if the stator is not round, the pole faces, as they rotate, will be again exposed to varying levels of magnetic flux, and that variation will cause circulation of current, and will increase the heat of the pole face. We had a case in Canada where I think the expected pole face temperature was around 65, and they did an uprating, and when we went in to do some testing, we found that some poles went up to 105 degrees C. So that was a big surprise to everyone. So if you change the electromagnetic conditions, whether it's an uprating or you have a stator that's not round, you can produce overheating poles that will wear them down quite quickly.
Thank you. We have another question also from Mark Bissonnette. From your diagnostic experience and your ZOOMWatch severity charts, are you finding more issues with rotor, stator, or bearings, or other?
Well, we find issues, I would say, whenever we find issues with bearings, in many cases it's because of the dynamics that we see from the rotor and stator. People will focus on vibration and will immediately think about film distribution, oil distribution. We'll think about gapping. We'll think about the alignment and all, which is all fine. But in many cases, we see that when we see very high vibration levels, it's often caused by the dynamics in the air gap. So either the rotor is out of round, or it's not centered, or the stator is out of round. I have to admit that in most cases it's both. Of course, the stator is although it's static, people are always amazed to see everything that you can observe. Stators that don't expand correctly because of seized sole plates. I mean, sole plates are probably the most under-managed or under-maintained component of a hydro generator. Those and compression bolts for the stator, those are neglected and nobody pays attention. And when we show up and take tests, we can see that one section of the stator is just unable to move. And if that's the case, well, the rest of the locations are going to compensate, and then you end up with stators that look like clover leaves, or they look like peanuts, or we see all kinds of shapes, and they're very easy to see. But I think the biggest issues we find, and maybe we put more of an emphasis on it because it's a rotating part, is rotors, rotor poles, rotor rims. My department pays very close attention to that, because if you do have an issue there, the fact that it's rotating and being subjected to centrifugal forces, very strong electromagnetic forces, things can go very wrong there very quickly and cause a tremendous amount of damage. Whereas if you have a seized sole plate for a stator, I mean, it's an issue. Usually it's easy to solve, but the sole plate is not going to cause a major damage to the unit, not in the short term. So I would say we see more serious issues with the rotors. Yeah. But we do see serious issues with the stator. One famous case in Brazil where we showed that the stator moved downstream. That raised a lot of eyebrows. When they applied the field, the unit would actually move downstream. But that's, as you can imagine, quite uncommon. And we do see a lot of issues with bearings and shafts and misalignments. Yeah, you do see quite a few of those. So all of these can be monitored. We have phenomena, severity levels, operability levels for all of these different parameters on the unit. And when you do get a report, you can go to your account on the web, on the ZOOMWatch platform, and take a look at the results. And if you see some results which are interesting, you can click on the report, as I mentioned before, and get a complete detailed report as to what's going on, what we've observed, why we feel this is excessive based on, in many cases, existing standards. Some cases it's our own standards. And then we have recommendations on what they should do about it. So I think it's a complete package. And we have we have more and more customers using it. And the key for me is that they are all renewing their contracts. So that's a very good sign that they enjoy the service and want to keep getting this valuable information.
Thank you. We have another question here. I always thought that end-winding vibration was a turbo generator issue. Why monitor end-winding vibration on hydro generators?
That's also a good question. Yeah, I mean, historically, most of the fiber optic sensors that we provide, and we have quite a few different models for insulation class and one direction, two direction. It has been mostly used on turbo generators simply because they have the most issues with their end windings. The turbo generators have, of course, they're 99.9% horizontal. I was questioned about a vertical turbo generator in the northwestern United States, and the engineer actually sent me some drawings to prove that they had a vertical issue. So I used to say all turbo generators are horizontal. I stand corrected.
There are a few small ones that are vertical, yeah.
Yeah, very old ones too.
Yeah.
So the fact that the end windings on these units are very long, and since they're horizontal, well, gravity is actually pulling on them. And when you actually run the unit, then you introduce electromagnetic forces. If you have resonance issues, there's all kinds of forces that will come into play that can cause issues on the end winding. Some of them are 2 meters long. So the consolidated basket, it's difficult to maintain. It's difficult to make it very stiff so the vibration doesn't occur, or is limited, but also very flexible to allow for the expansion and contraction based on the heat which is present. So they have many more issues on their end windings than on hydro. However, we've been installing on hydro generators and also on motors in the mining industry because we find there are issues on those as well. One famous case that I worked with a couple of engineers at Rio Tinto Alcan, and a paper was published on that where they had serious issues with one of their, if I remember, they had 11 units. It was built to provide power for the aluminum smelters for the efforts for World War II. At that time was one of the largest, if not the largest, hydropower station in the world. And they had one unit that consistently had winding failures. They would bypass stator bars. I think in the end they had like 17 bars which they bypassed to try to keep the unit online and producing power, albeit it was reduced power. They couldn't go full power. And they couldn't understand why this unit was having so many issues because they didn't seem to have these issues with the other units. And in reality, they installed the same equipment on another unit just to have a reference. And it confirmed that this particular unit had serious vibration issues, and also corroborated with some thermal mapping that they did to look at the power, and they could see the insulation was deteriorating. It was getting hot spots everywhere. And in the end, they were able to use the fiber optic accelerometers to try to understand exactly what was going on. And an interesting thing they did was this power station it's common for this power station to run out of water during the summer. And they could see the vibration of some of the windings increasing significantly. I think one was up to like 9 Gs at 120 hertz, which is significant. And they used this stoppage, this outage, to go in there and stiffen the windings, to add support blocks, to remove ties, put new ones, use the wet ties, which are much better to hold the windings in place. They did a lot of work. And when the unit was restarted, I believe 3 weeks or a month later, they were very happy to see that the vibration had decreased significantly. But they were also very surprised to see that adjacent windings on which they had sensors, but they had not worked on, also showed reductions in vibration. So that goes to show that when you monitor end winding vibration, because of the cost involved, you're limited to the amount of sensors you can put. And if you see vibration that's high in one location, you have to remember that may not be the highest level of vibration on the unit. So you can't say, well, the vibration is so much, it's high, but not the end of the world, we can live with it. You should go in there and do an inspection, because it is possible that the vibration you're picking up on bar X is actually being generated by bar Y, which is adjacent to it, and is vibrating tremendously. So it was an eye opener for them, And the paper was published quite a few years ago at the CGRE conference, if I remember correctly. So it is more popular on turbo generators because of the issue. They have more issues, so using fiber optic is more common. But there are quite a few hydro and quite a few mills, ball mills and sag mills in the mining industry that use this type of technology to try to avoid major failures at the end winding level.
Thank you. We have another question here, and I think that this question has to do something with the previous one. I've heard you mentioned a combined velocity temperature sensor to monitor bar in slot vibration in one of the technical tips video clips on YouTube. Could you explain what is this about?
Yeah, I did touch upon it a little bit before. That's a good question. When looking at either end winding vibration or phase leads or phase drops or the entire electrical circuit, and also looking at stator bar vibration, stator bars in the slot. We have, as I mentioned, the fiber optic technology to look at the high voltage locations, and we have a capacitive probe, quite a few capacitive probes that can actually look at the vibration of the bar inside the slot. However, hydro generators, as we all know, have hundreds of stator bars. And it's just to be able to monitor all of these bars, the costs involved have always been a huge stumbling blocks. You had to make decisions as to where do you think there's the highest potential of vibration. Are there any visible signs that there is vibration already present that we would need to focus on? If you have 400 bars, there's no way that you can put 400 fiber optic sensors. Just the cabling would be a nightmare, and the cost would be astronomical. It'd probably be more efficient just to replace the windings at that point. So that has always been an issue. We worked around it. We tried to find the best coverage possible, and to resolve this issue, our R&D department has come up with a new sensor, which is basically a series of 100 sensors on a communication line. And those sensors are able to provide you with the absolute vibration and temperature of the bar. So you can put these sensors, you can cover all the bars with which much more cost-efficient manner, and it allows you to output either acceleration or velocity, whichever you choose, and the temperature. So you can corroborate, or you can compare vibration levels to temperature levels. And then we feel this is a very elegant, very non-intrusive approach to be able to give you the best coverage possible for the entire windings on the stator core, and give you a first level assessment as to, okay, do we have issues? Do we have serious problems that we need to invest in to prevent a major failure? So it's a very, very cost effective. I think it's a very elegant solution.
I would say that's a breakthrough.
So yeah, we're very, very happy about it. We're looking forward to seeing this be deployed everywhere and start getting results. I'm sure we'll find a lot of very interesting results.
Thanks, André. I have another question from André Bissonnet. Have you seen cases where machine design and condition is good, but can be negatively impacted by startup of the machine? In parentheses, standstill to speed no load, time settings of speed governor.
Yeah, yes. The first one that comes to mind is there was a power station in Brazil where the OEM had offered 4 units with a new rotor design. It was new at that time. Basically, the design was that the rotor rim would be tight, would be a shrink fit, but if the unit reached 110% speed during an overspeed or load rejection, the rim would be allowed to float to absorb the energy. So the design was simple, but at that time this was a new concept. So the utility said, okay, we will buy into your design, but you will put 16 air gap sensors on each of the stators, 8 at the top and 8 at the bottom, so that we can validate that your design works as promised. So they did, and I actually went to site 1 year for the original commissioning. And I remember I was in Brazil, and it was probably one of the worst colds I've ever had. This is
In
the last
Brazil?
time, yeah, last time I've ever gone anywhere without looking at the Weather Channel. For me, I was going down to Brazil, so I had my Bermuda shorts and my
you went to the
t-shirts.
south, probably.
Yeah, and I got there and it was 5 degrees in the day.
Yeah,
and
close to Argentina.
Wow. So we did a whole bunch of testing, and of course one of the first things they wanted to do was do an overspeed test. So they brought the unit speed to 150%, which was like 100 and, in fact it was a little more, I think it was 138 RPM. I talk about this case in our training courses. And if you looked at the result, you could see that as they slowed down the unit, at 138 RPM, you could see the rim was floating. The rotor shape varied significantly, but that was normal. That was the design. And as we decreased the speed, you could see the air gap increase because the rotor was slowly going back to its original shape. And you could actually see the moment where the rim would go back to a shrink fit. You would see the shape of the rotor decrease significantly at one moment in time within a few rotations. So if you looked at those results, the first impression you had was the design works exactly as proposed. I mean, the rotor rim would float at high speed, and at slow speed, it will go back to its original shape. So everybody was celebrating, high fives, everybody making meetings to go and have a beer and celebrate. And I had a cold, so I said, no, I think I'll skip the drinking part. And I just sat there for hours looking at the results. And at one point, I discovered a huge problem. And I use this in case studies during the training courses because it's a good example in paying attention to the details. And sometimes the most compelling information is not where you're looking. We are so used to analyzing data and looking at it from this point of view. And we tend to forget to look at the whole picture. And to make a long story short, yes, the rim did go back to its original shape, but nobody had noticed that it did so at 78 RPM, which is actually less than the operating speed of the unit. It should have gone back to its original shape at 99 RPM. So when I showed this to the commissioning engineer, he quickly saw this was a huge issue because it meant that technically the unit, the rotor rim could become loose during normal operation, which of course would be a total disaster. So they got the OEM involved, and the OEM was very good. They looked at all the data, they contacted us on a regular basis, and they went back and they changed the constraints for the rotor rim, applied their corrections, did the test again, and the unit was fine. So again, use of information at the original commissioning stages to fix issues and to be able to make sure that these units will be working for long periods of time. So we do have cases. I have another case where this is, again, looking at the results. It was another power station in Brazil quite a few years later where we were doing some tests, commissioning the system and the unit, and I picked up a startup. And if you looked at the startup at full scale, it looked completely normal. We're used to seeing where the air gap decreases because of the centrifugal forces, and it looked perfectly normal. But if you zoomed in to the initial rotations, you could see how the rotor was significantly distorted. I mean, if you looked at the rotor shape from different sensors, it was completely different. And that's a clear indication that the rotor was distorting, so it had a different shape depending where you were looking. And eventually, when it reached full speed, it was fine. And when I showed that to the engineers, they made some verifications, and they found that someone made a mistake and had configured the governor system to accelerate much too fast to reach nominal speed. Something like it's supposed to take 85 rotations before it reaches full speed, and it was configured to take like 55 or 58. So the unit was put through a tremendous amount of stress needlessly. It was just an error. Now, if we hadn't taken the measurements and noticed this, it would have probably gone on unchecked, and eventually they would have all kinds of rotor issues, and they would all wonder why this is going on. What's the problem? And the problem was simply the configuration of the startup. The machine just accelerated too fast, and that was corrected, and the machines are fine.
Thank you, André. We have another question here. Yes. You've mentioned axial displacement in the past. Do you have any examples of issues with actual vertical displacements on hydro generators?
Yes. In fact, we've had a few. There's a power station not far from here that had bearing failures, a couple of bearing failures within a very short period of time. And turns out that the rotor was installed too high. In many cases, the rotors are slightly lower than the stator, so that when you apply the field, it's actually going to lift the rotor slightly, giving the truss guide bearing or the combined guide bearing a little slack, a little less stress to hold the unit in place. The case that I'm thinking of was in Canada also. They had a major failure, and they had spent 60 days non-stop fixing the problem. The unit had been dismantled, they reinstalled the unit, and we had installed air gap sensors, shaft displacement probes, and one axial probe. But when the unit was commissioned, tests were performed, but obviously all the engineers, all the technicians, all the mechanics, everybody had been working 18 hours a day for 2 months. So when the unit was back online, everybody disappeared. Everybody took vacation time to relax and rest. So the data was never actually sent to us. And well, unfortunately, I think it took like 3 weeks or a month. Eventually, the truss guide bearing failed again. So the utility sent us the data and said, well, could you take a look and see if you can spot anything that happened while this occurred? And what happened is that we could clearly see that the axial displacement probe, which was below the coupling looking upwards, could easily see that as they were increasing the load, the gap was going down and down and down. So water was applying a tremendous amount of pressure on the unit, hence on the truss guide bearing, which is normal. I mean, you do expect to see more and more pressure, but the levels that we were seeing were way too high. And actually, you could see if they ran the unit in synchronous condense mode, the unit would lift up tremendously because, of course, there's no water anymore. So we showed them the results, and it was clear that the unit decreased in height or went down vertically at a much greater rate than what it was supposed to. And it turns out apparently the turbine was installed too low or something like that, and the water was actually able to go on top of the turbine and push down on it. So that was fixed, and the truss guide bearing was functioning properly. Yep.
Thank you. Well, we have another question here. Are VSM monitoring systems, VSM stands for vibro system, also used to monitor very large electric motors?
Yes, we do. As I mentioned before, we've been doing so for, I don't know, maybe 8-9 years. We've been involved with mining companies mostly in South America, but elsewhere in Asia and in the US, where we've been monitoring or offering monitoring solutions for large sag mills and ball mills. I mean, other than the fact that they're horizontal, that they don't have a shaft, and that they are at very slow speed, the rest is pretty much the same as if you look at a large hydro generator. Again, the frequencies are different, but it's still stator bars, it's still insulation, it's still stator cores, stator frames, poles, interconnections, bearings. It's basically very, very, very similar, and we've been very fortunate to work with mining engineers, very competent mining engineers, and we've helped them significantly find all kinds of issues on their units and try to improve their performance. The mining industry produces tremendous amount of revenue, and long unexpected outages are a tragedy to them. So, well, it's a problem to everybody, but in their case, it's a lot of money. So they do not want to stop their mills for no reason, and when they go through outages, they want those to be as efficient as possible to put these units back online. So we found all kinds of temperature issues, vibration issues, bearing oil film issues, serious rotor pole issues, serious stator core and frame issues, and we've actually started to help them replace their poles. We've developed a technique to where we can actually help them replace all the poles on their rotors, and with our air gap sensors we can help them make sure they're all radially symmetrically positioned all the way around to make sure that the poles are in the correct position. We can do the same for the stator. We've done that, I think it was in 2019, where we helped this customer do a major replacement of all the poles and a replacement of the stator. And I mean, they cut the downtime like 10 days, which for them is millions of dollars, just by having better technology and better tools to help them do this. So we've worked very hard and plan on doing so in the future. It's a very interesting field for us, and it's also very interesting when you see that you can actually help these people tremendously, not just provide equipment and work, but actually help them get a better grasp of the issues they have, give them hope that they can improve the performance, improve the lifetime of these units, which is usually surprisingly very short. And we've helped quite a few of these companies extend the lifespan of their mills for years. So it's a very interesting field for us, and we're very glad that we have the opportunity to work with them in that.
That's exciting, yes.
Yeah.
We have another question here. How does cycling affect the lifespan of a hydroelectric generator?
Depends who you talk to. It's a well-known fact that people, I think, correctly assume that a lot of the damage that cycling does to not just hydro generators, but generators in general, is the cycling, whether it starts and stops or whether it's load cycling, it causes the contraction and expansion of stator bars and of the stator core and stator frame and all of these different components. So if you change the load, or if you start the unit from cold to hot, you create, because of the heat generated by the copper, dissipated by the insulation, and then dissipated by the core, it creates this expansion and contraction of the windings. Now, windings or insulation, epoxy mica insulation, has tremendous electrical properties. It's fantastic dielectric, but its mechanical properties are horrible. It's basically glass. And if you've shaken glass, shaken a mirror or a window, you can see that it can crack. Plus the fact that glass does not like to rub. So if you expand and contract, you will have this rubbing action going on. If you do it frequently, you will deteriorate the insulation. It's also been told that the changing of the heat will cause also insulation wear and tear. Now, I have seen a paper that discusses the fact that the most damage done on insulation is prolonged exposure to heat. Therefore, base load units will have insulation that will wear out faster than units who cycle. And the idea behind that is that what will deteriorate the insulation is, in fact, a prolonged exposure to heat, which will chemically alter the epoxy mica and will deteriorate. Now, of course, if you have a unit that's been operating as a base load unit for 20 years and damage has occurred, and then you start cycling the unit, well, that's even worse. That's really bad. And that's probably the reason why we have a lot of insulation failure or winding failure. So the cycling has an impact for sure. The cycling is now common because of the wind farms and the solar and all the renewable energy that's put on the grid. A lot of the utilities have had to change the way they operate, and it's introducing issues to these units, which is why we feel monitoring systems such as ours is critical. It's very helpful to be able for you to grasp what is the impact of all of this cycling, and maybe allowing you to intervene before failures occur. It's much easier to fix a problem than to have to fix the unit because it actually failed.
Thank you very much, André. I think that'll be it for today.
Okay. Well, thank you all for listening in. I hope you found it interesting. Don't forget to subscribe to our YouTube channel, and don't forget to ring the bell if you'd like to be notified when there's new content on the channel.
Also, don't forget to write your comments or questions at the bottom of the page after this session. We will answer them during the next Q&A session. The videos will remain permanently in our channel, so you can listen to them at any time in the future.
So if you'd like to contact us directly, you can do so by sending us an email at diagnostics@vibrosystem.com. If you'd like to have any information on installation, on specs, on technical details, you can also contact our service department at service@vibrosystem.com. Of course, if you need any information on pricing, on delivery, on commercial relationships, you can contact the sales department at sales@vibrosystem.com.
You can also contact us via the comments in the section below, or via our LinkedIn page or website, or via Facebook.
Okay, so if you do have questions that come later on, or you have a question and haven't had a chance to put it in there, just even if the session is over, you can log on, you can type your questions in, we'll log them, and we'll take a look at them and answer them at a later stage. So thank you all for listening in. Thank you, Paul.
Thank you.
For your logistical help. And I hope you'll all be there for our next Q&A session to be announced shortly. So make sure you log on or you check our advertising on LinkedIn or our Facebook page for the next date for our Q&A session. So be safe. Thank you all for being there. And bye-bye for now.
Take care. Be safe. See you next time. Hasta la próxima.